So, hello everyone. Good morning, good evening, good afternoon. Let's start our eighth lecture. Before we start our lecture, I will show you some videos from our sponsors. Okay. So first of all, from Professor Paulo Gamba.
Good morning, my name is Paolo Gamba and I am the president for the year 2020 of the Geoscience Remote Sensing Society. Okay, so first of all, what is a scientific society? What is GRSS? So a scientific society is a group of scientists, researchers and practitioners with common interest and common framework for building a community. In our specific case, we are people who are dealing with theory, concept, and techniques of science and engineering as they apply to remote sensing of the Earth, ocean, atmosphere, and space, as well as the processing, interpretation, and dissemination of this information. So what are the activities of the IEEE Geoscience and Remote Sensing Society? Well, we have a number of applications. We support conferences. We have professional activities. We have a number of information service and technical activities and education activities as well. We are a global community, which means that we are arranged around a large number of groups of people that we call chapters all around the world. We have currently more than 90 chapters all around the world. As a result, GRSS disseminates premium science by means of its three main journals, which are the Transactional Geoscience Remote Sensing, the Geoscience Remote Sensing Letters, the IEEE Journal of Selected Topics in Applied Earth Observation and Remote Sensing, but we have also a magazine, which, by the way, has a very, very important role. We also provide opportunities for the different communities, like, for instance, the community working on image analysis and data fusion. We also sponsor community-driven events, like the very successful Earth Vision workshop, but also the SpaceNet Challenge data challenges here, which is organized by SpaceNet. We support also community-developed tools like the DESE website, which is Data and Algorithm Standard Evaluation website, and also activities related to RFI observations. So we also facilitate and connect. We have a number of activities at in our main conference. We have the so-called TIE events, but we also organize different events related to connection with companies, industries. We have a number of activities like for young professionals, for women in engineering and in geoscience and remote sensing. And we share our knowledge on hot topics by means of distinguished lecturers and industry speakers. We have also a number of educational activities. This is one of them. This is basically, let's say, one of the many different small educational videos for kids that we have in different languages, but we have also, in addition to that, a number of webinars, which are also for people who are not kids, about remote sensing in different languages as well. We offer continuing education by means of webinars, which is especially important and useful in this situation where we are not able anymore to move around the world as we were in the past. So we can support continuing education of students and young professionals through conferences, journals, our magazine, webinars, and so on. We can promote capabilities of the different communities, algorithms, data set by means of the data fusion context, by means of dedicated events at our conferences, by means of the industrial distinguished lecture or industrial speakers. We help connect companies and young motivated people by means of the young professional event, by means of student grants, by means of the TIE forum. And we make the different community of Earth observation practitioner and researcher be aware of their and your topics of interest. So GRSS is actually a community of communities where we could together share and promote ideas, systems, and dataset. We can meet with other communities and gain from their perspective, and we can build different collaboration to learn more from each other's and to come together in conferences. Thank you very much, and I hope you will enjoy this summer school and all the interesting topic and talks that you are going to listen during these days.
Thank you, Paolo. So let's see some words from Sherry Hayes from ISPRS.
Hi everyone, my name is Cheryl Rose Reyes, and I currently serve as the president of the International Society for Photogrammetry and Remote Sensing Student Consortium. I am very happy to welcome you all to the 6th edition of the IEEE-GRSS Young Professionals and ISPRS Student Consortium Summer School this year. To start this event, I would like to present a bit about the ISPRS Student Consortium. We are the official representation of the youth to ISPRS. We link students, young researchers, and professionals worldwide interested in photogrammetry, remote sensing, and spatial information science to promote their scientific and professional developments. We advocate imaging and geospatial science for informed, scientifically valid, and technologically sound observations of Earth conditions and trends that lead to improved and effective decision making. The consortium is also accepting registrations for individual membership. Please scan the QR code in this slide if you are interested to join us. I work together with members of the board of directors from all across the globe. Charles from Uganda is our vice president. Charmaine, who is currently in Ireland, is in charge of our newsletter. Mustafa, our social media administrator, is from Turkey. And finally, Sona from Azerbaijan is our web administrator. One of the major events that we host and coordinate every year are the summer schools. In 2019, the summer schools were in Uganda, Poland, South Korea, and Brazil. These summer schools provide international learning opportunities for students and young professionals at a minimum cost. This year, we scheduled 3 summer schools, but due to the COVID-19 situation, 2 of them were postponed, and we are sincerely thankful to the organizers of this summer school for making this an incredible virtual event. This is the first ISPRS Student Consortium Summer School that will be hosted online, and as you can see, we have an amazing lineup of speakers who will deliver lectures on remote sensing and machine learning. The consortium currently hosts the virtual rooms and the webinar series to provide our community with more opportunities to learn and interact with experts in our scientific community. The webinar series was conceptualized in 2018, and we have organized webinars on Google Earth Engine, computer vision, and machine learning. The virtual rooms is an initiative to keep the members of the consortium connected during this challenging time and to help them navigate our changing lifestyles. All the resources for the webinar series and the virtual rooms are available on our website and our YouTube channel. We also publish an official newsletter called Spectrum, which covers the broad applications of remote sensing, photogrammetry, and spatial information science, and welcomes contributors from diverse backgrounds and disciplines. We publish 4 issues a year, and our most recent issue is related to the current pandemic and the significance of geospatial information in tackling the impacts of this global health crisis to our society. The ISPRS Congress is one of the biggest gatherings in our scientific community, which is held every 4 years. The Congress hosted a virtual event for all papers submitted this year and postponed the in-person meeting for 2021. During the Congress, the consortium will be hosting a 3-day youth forum, which will feature the following activities: speed dating, technical sessions, a special session on women in remote sensing, photogrammetry, and spatial information science, a panel discussion, the General Assembly for our members, a student night, another summer school, and will co-organize a mapping party. The consortium would also like to invite you to nominate papers for the Excellence Award to be given during this event. Please scan the QR code for eligibility and nominations. Also, please visit the ISPRS Congress official website for updates. Finally, I would like to invite you all to join our communities on Facebook, Twitter, and to visit our website for all the information shared in this presentation. And again, I would like to invite you all to register as an individual member by scanning the QR code on the right. This is the end of my presentation, and I wish you all a meaningful summer school. Thank you very much.
So thank you, Dario. And now let's start our session. I would like to invite our colleagues. First of all, Professor Philippe Maillard. It's my colleague here at Universidade Federal de Minas Gerais, and also our student invited, Laura Helena from PUC-Rio. So thank you for accepting to share with me this nice task of conducting the lecture, the session. Okay. So Philippe, could you please introduce our speaker, please?
Okay, yeah. Hello, Jefferson. Hello, everyone. We're going to start our session with Mauro Dalla Mura. Mauro was, if I can, Mauro received a bachelor and a master's degree in telecommunication engineering at the University of Trento in Italy. He then pursued a PhD in information and communication technologies at the same university, but also it was a joint PhD at the electrical and computer engineering from the University of Iceland. Okay, his talk will be about image fusion, or Pansharpening, as it might rightfully called. So he will do a kind of overall perspective on the Pansharpening issue, and then afterwards we'll have a 30-minute discussion. So Mauro should take up to about an hour, I think, for his presentation, and then we'll have a period of questions and comments. So welcome, Mauro. It's a pleasure to have you here. We're very honored to have you for this presentation. And without anything less and anything more, I will pass you the word so you can start your presentation.
Okay, thanks Felipe for the nice introduction, and I would like to thank all the organizing committee, Jefferson, Veraldo, and all the other colleagues for this invitation. And it's really a pleasure to be part of this summer school. And so it's a pity that it's not that we could not do it like live in person. But like anyway, it's good to gather together even remotely. So I'm going to share. So my screen is shared. I'm going to put it in full screen. So now I think you should see my slides in a full screen. And then so if it doesn't work, just shout, and I will try to get back on that. So the talk that I'm going to give is about Pansharpening, and the idea is to provide an overview on the topic and some perspectives. So let's start with the presentation. And like Pansharpening deals actually with very high spatial resolution optical images. So here you see an example where we have images acquired by satellites that have a very fine resolution, and we see very precisely like small spatial details. And for example, here you have a comparison between images acquired with let's say, a spatial resolution of about 30 centimeters. So that is what we call a ground sampling interval or ground sampling distance. So that basically the footprint of a pixel projected on the ground. So that is about 30 centimeters squared. And here, for comparison, you see an example of an image acquired with a coarser spatial resolution that is about 70 centimeters. And so it is easy to see that higher quality in terms of the rendering of the spatial details is provided by having images of higher spatial resolution. And if we have a look to the panorama of the different satellites that are present and orbiting around the Earth and acquiring images of very high spatial resolution, we can see that we have really a lot of them. So, for example, here you see some examples of very high resolution satellites that are coming from the Earth Space Agency, and like data are distributed by Airbus. And here you see some constellations that are owned and handled by Maxar, and they all provide images of very high spatial resolution. So let's see now what we can do with this kind of very high spatial resolution images. So as you know, there was like a very sad event in Beirut, Lebanon in August 2020, where like there was a big explosion in the harbor, and more than 100 people died, and there were several thousands wounded. And here you can see an image acquired by a very high spatial resolution satellite, which is WorldView. This is a satellite from Maxar, the Maxar group. And here you can see an image acquired before the event. And now you see an image acquired after the event. And we can see that by having at our disposal images of very fine spatial resolution, it is possible to give in a short amount of time an assessment on the damage that was caused by this event. And here you have another example. So here we have another part of on the harbor. So the image was acquired before the event. And here we can see what happened afterwards. So as you can see, this kind of imagery is fundamental, is really pivotal for gaining some information in a quick way and allowing to assess what are the consequences of like a natural hazard, or like to finally monitor some resources, or like some human activities and so on. So having at our disposal images that are that have fine resolution is really important. So if we want to acquire such images, or like in order to perform some fine analysis on those scenes, we can like look on catalogs and like order them, or like looking into archives and so on. And by doing this, it is possible to see that we have different products that are offered. So those very high spatial resolution satellites acquire images that are of different characteristics in terms of spatial and spectral resolution. And by the data that are offered by the data providers, we can see that there are some products that are related to Pansharpening. So that was an example from Maxar, and then this is another example from the company Airbus that is providing images of very high resolution from satellites, for example, that were launched by CNES, the French Space Agency. And so we can see that, for example, this is the case for the satellite Pleiades. And we can see that we have different products, as I mentioned. So the basic raw acquisition is a panchromatic image of like spatial resolution, in this case of 50 centimeters, and a multispectral acquisition, a multispectral image, having a spatial resolution of about 2 meters. And this provides for different spectral bands. So a blue, green, red, and a band in the near infrared. So this is kind of a raw acquisition, like images that were acquired and not processed by, or like at least with some pre-processing, but they are offered to users. And then it is possible also to have some other products. And those products are, for example, Pansharpened images. And we can see that we have different kind of those products, like using 4 bands or 3 bands for having like a natural color image and so on. So it is possible to underline in this case that like images, again, as I mentioned, like they are coming in 2 different formats in general, and it is possible to acquire or like to generate images of higher spatial resolution in terms with respect to the multispectral acquisition. And those are the so-called Pansharpening products. So if we now focus on like Pansharpening, so what is Pansharpening? So as I mentioned, like those satellites that I presented before acquire usually a bundle of 2 images. One image acquired by a panchromatic sensor that will look, for example, like this example that you see here. So this is a monochrome image, which is actually acquired by a large band sensor, showing very fine details that are present in the image. So the spatial resolution of this image is higher than like the companion multispectral image. So this multispectral image is acquired by another sensor that is equipping the same platform. So those 2 sensors are mounted on the same platform, and this multispectral image shows some spectral diversity because we have different spectral bands, and we can see that the spatial resolution is lower with respect to this image here. So in a nutshell, what is Pansharpening is like the process of fusing a panchromatic image and a multispectral image in order to have an image which has the bands, the spectral information coming from the multispectral image, but the details coming from the panchromatic image. So again, like we have those 2 raw images, and we would like to fuse them in order to obtain this Pansharpened image. So the presentation that I'm going to give is based on a collaborative effort of like providing a unifying framework where we can cast several Pansharpening algorithms that have been proposed over some decades, and the sources of this presentation are contained in like 2 main publications. So the first one was published in 2015, and so you have the reference here. And there's a new one that just got recently accepted in IEEE Geoscience and Remote Sensing magazine that is giving some updated information on such a survey. So if we start to get more in depth in what concerns the Pansharpening algorithms that are present in the literature. So Pansharpening is a very active area of research in remote sensing. So like if you go on IEEE Explore, for example, and you search for Pansharpening, you will see like many hits coming out in terms of conferences and journal papers. And if you have a look to those papers, you will see that there are a plethora. There are really several methods and several different algorithms that have been proposed. Because as I mentioned, this area of research started more than 30 years ago. So there are several decades in which researchers and practitioners have proposed different techniques for performing such a sharpening of the multispectral image using the panchromatic information. So the idea of this presentation is to provide for what we call classical algorithms. So the main algorithms that can be considered as kind of baselines to provide a unifying framework where we can define them, and that will ease their presentation and also their comparison. So let's now start to give some more details on these Pansharpening techniques. So as I mentioned before, the goal of Pansharpening will be to fuse those two images in order to get a higher spatial resolution multispectral image using guided by the details that are present in the panchromatic image. And this is actually a problem which is ill-posed because there are several different solutions that we can provide here that would satisfy somehow the problem of using a panchromatic and a multispectral image. So the problems, the main limitations or the issues that we need to face in order to generate such synthetic image of high spatial and spectral resolution are related to the fact that the spatial details that are present in the panchromatic image, they are not visible in the multispectral. And what we see in the panchromatic image doesn't show any link to the spectral bands, providing this spectral diversity that here is shown, is represented by different colors that we see in the multispectral image. So basically, by looking at this gray level here, it's difficult to guess that was due to these kind of materials with a given reflectance that will provide a radiance that in the visible domain looks like this. So we might have ambiguities in that. So this is not an issue for those large areas, but can be an issue for the small details that are resolved here, so we can see them, but we cannot see them in the multispectral image. So just to fix some main concepts that will be useful in the following. So when as we are dealing with images of different spatial resolution, as you can see here, what is usually done is to model this reduced resolution that we can see that is shown by the multispectral image with respect to the panchromatic image, could be modeled by a convolution of the, let's say, unknown multispectral image of higher resolution with a given kernel, with a given mask. And that mask can be associated to the impulse response of the multispectral image, which is usually called the point spread function. So basically, in this setting, we could consider the panchromatic as being kind of a perfect image in terms of what we associate with the possibility to resolve in a good way spatial details, and the multispectral image, conversely, if we have a look, if we perform the same in terms of analogy, if we do the same, if we present the relationship between the panchromatic and the multispectral from the spectral domain, the multispectral will, as I mentioned, will show this spectral diversity due to the fact that we have we sample the spectral domain of light in different intervals. And those will not be the case for the panchromatic, because there will be an integration over a large domain in the spectral domain. So if we now go on, and we can now present what are the main approaches that have been proposed in such like a huge amount of works that have been have appeared since the early 90s. So there is actually a main model that we can define, and we will see that this model here that I am going to present it in a while will be like a kind of a general model that we can find that we can find it in different algorithms under, let's say, slight variations. And that was one of the main goals of those works that I mentioned, like try to find a unifying framework. So here, in terms of notation that will be used in the following, we denote by M hat the result of the Pansharpening for a given band. So that would be one of the band of the synthetic image, showing about high spatial and high spectral resolution in terms of with respect to the panchromatic and the multispectral image that we have. Then we will have M tilde, which is a multispectral image. So the original acquisition that we had from the sensor, that will be upscaled because, as you saw before, as we see here, the scale, so the spatial dimension of the multispectral is smaller than the panchromatic image. So usually this is 1/4 of the spatial domain of the panchromatic. So there will be an operation performing an upsampling, an upscaling, without any further processing of the original multispectral image in order to match the scale, the spatial dimension of the panchromatic image, and then also the final result that we are looking for, so the Pansharpened image. And then like our panchromatic image will be denoted by P. So this is just a scalar image. And the idea is to try somehow to extract some spatial details from this image here. So some spatial features that are resolved by the panchromatic image, but they are not present in the original multispectral image. So basically, this general model that we can see defined here tell us that the result of Pansharpening for a given band K is equal to basically the sum of an upsampled version of the original multispectral image for the same band, in which we add the spatial details that are obtained from the panchromatic image with some injection gains, so with some weights. So those this term here, this coefficient, will weight how much details we will like inject in the original multispectral image. So as I mentioned, like the effort that was done with those two papers was to try to put all those different algorithms that have been proposed in the literature and show that they all belong, they can be all represented by such a model. And in the following, we will see that the classical approaches can actually be divided into families. One family is called component substitution, and the other family is called multi-resolution analysis. So for the first family, what differs in those two is the way we actually estimate the spatial details from the panchromatic image, and we will see that different algorithms will define like these spatial details in different ways, and will define the injection gains in different ways as well. So the component substitution will estimate the spatial details based on some information coming from the multispectral image, whereas the multi-resolution analysis will perform an estimation of the spatial details from the panchromatic image. So I will tell you a little bit more in here. So like if we take the component substitution family, we can see that the spatial details coming from the panchromatic are obtained by performing a subtraction from the original panchromatic image. So this is the original band, the original panchromatic channel that was acquired by the satellite, where we subtract this IL. So this IL is actually an image, a monochromatic image, so a scalar image as well. So same, it will be defined in the same domain of the panchromatic. And this monochromatic image can be associated as a kind of an equivalent of the panchromatic image obtained by a linear combination of the spectral bands of the multispectral image. So you can see here that this I term is given by the linear combination of the original bands upsampled of the multispectral image with some coefficients. And we call this family component substitution because like historically, those techniques were proposed were following a procedure where the multispectral image was transformed into another representation space, in which the idea was to try to decouple the spatial information from the spectral information. So the spatial information, meaning like that would be kind of a component in the transformed space where that should match more or less the panchromatic image, because as we mentioned before, panchromatic image will be a broadband acquisition on the spectral domain. And the idea in those early representation of the component substitution analysis techniques was to perform such a transformation, then identify the component that was bearing the spatial information, or let's say the component that should be close to the panchromatic, and then substitute the original panchromatic image to that component and apply get back to the original space, so apply a reverse transformation in order to spread the higher spatial resolution component that was substituted into the different channels of the multispectral image. And it is possible to prove that actually this procedure is equivalent to the technique that the formulation that is provided by this simple equation. So if we have a look to like a more general view on the flowchart of these component substitution techniques, we can see that we have several blocks. So this is kind of like a representation showing several different processes that we can carry out, and basically the multispectral information, the multispectral bands after upsampling, they will get combined. They will get combined by this linear transformation in order to have an intensity image provided. And this intensity image will be subtracted to the panchromatic image that could be matched in terms of dynamics with respect to the dynamics of this linear combination of the multispectral bands. And that will show basically the details that are present in the panchromatic image, but they are not resolved in this linear combination of the multispectral bands. And those details will get injected, they will get added to the original panchromatic image in order to provide a final pan-sharpened image that we have here. So if we go now, if we take into account the second family, which is called the multi-resolution analysis, as I mentioned before, this is using exactly the same formulation. The only difference with respect to the component substitution techniques is given by the way we define the spatial details coming from the panchromatic that will be injected by this additive scheme to the multispectral image. And in this case, the spatial details are given by the subtraction of the panchromatic image with a low pass resolution version of the panchromatic image itself. So basically, that will be a kind of a high pass filter. And this PL, so a low pass version of the original panchromatic band, is obtained by performing, for example, a convolution of the panchromatic image with a given kernel, with a given mask, that will provide this, that will blur, that will reduce the spatial resolution, so the capability of this image to show some fine details in the spatial domain. That should be, if you think, matched. It should be close to the spatial resolution of the multispectral image, because the idea is that panchromatic, so what we have here coming from the panchromatic image, should contain all details that are not present in the multispectral image, but they are resolved in the original panchromatic image. And if we have a look to the flowchart implementing the techniques belonging to this family, we can see, as we saw before, that we have like the multispectral image that will be then used for as a base for the sharpening. And then from the panchromatic image itself, we will generate a low-pass version of it. And by the subtraction of this low-pass version from the panchromatic, we will obtain the spatial details that will get eventually injected in the multispectral image in order to generate high spatial and spectral resolution multispectral image, which is the Pansharpening product. So if we have a look to now, if we focus on the injection gains, so the coefficients that will weight somehow the spatial details that will get injected in the multispectral bands, there as well, there are different approaches that are proposed in the literature. So some of those account for those injection weights as being scalars. So they will be the same. So they will be the same for all pixels in the same band. And some of those, some other techniques are actually defining these spectral injection gains as being pixel dependent. So we will have a single injection gain that will be different, possibly different for the different pixels that we have in the image and per band as well. So let's now present some examples of the techniques belonging to the two families, and we will see that how recalling their definition as they were presented in the literature, it is possible to see as those techniques all can be all casted in the general formulation model that we proposed before. So perhaps one of the simplest technique, or one of also of the earliest technique that was proposed, because you can see that some of the examples of this technique was proposed in the 90s, is based on what is called a generalized intensity hue and saturation transformation. So the idea here is that such a transformation that you might know that transform, like for example, an image, a color image defined in RGB color space into another color space, which is closer to the perception that we have in terms of colors, in terms of brightness, and so on, which is given by the so-called hue, saturation, and intensity color space. And in that color space, the intensity component contains some information coming from the brightness of the scene, which is kind of achromatic, so it doesn't depend on the different spectral characteristics related to the chromatic information that we can perceive as colors. And this chromatic information will be contained in the hue and saturation channels. So here the idea is that in this component substitution, let's say, scheme, this transformation can lead to components that decouple the spatial and the spectral information coming from the image. Then what we can do in these settings is that the intensity component of the hue, saturation, intensity model should be close to the information that we have coming from the panchromatic. So in this case, those early references propose to perform such a transformation, then substitute the panchromatic image with the intensity component of the intensity, hue, and saturation model, and get back to the original RGB space. So the generalized intensity, hue, and saturation model basically extends this idea in order to be able to process images of more than 3 bands. So we have a kind of generalized intensity, hue, and saturation transform. And if we cast that in the general formulation model that we have, we will see that we can define it in such a way, where the injection gains will be just 1 for all bands, and they will apply the same to all pixels. And the IL, so this intensity component, which will be kind of the equivalent of a lower resolution version of the panchromatic, will be obtained just as the average of the different channels of the multispectral image. Another notable technique, very well known in Pansharpening, was proposed, is what we call the Proby transform, and that was proposed in even before in 87, and that was proposed and presented by performing Pansharpening using an injection scheme which was multiplicative. So its initial formulation is given by this equation, where we can see the Pansharpened image is provided by the ratio between the panchromatic and this intensity channel. So that ratio will be performed pixel-wise. So every pixel in the panchromatic will be ratioed, will be divided by the value that we have in the intensity, this intensity channel here, linear combination of the multispectral images that we have in the corresponding pixels. And then we will have an Adamar product, so that will be a pointwise product as well, with the original multispectral image. And basically this scheme can be recasted in the general formulation model that I mentioned before, where the injection gains, so the coefficients that we use, are provided by such a ratio. So in this case, the injection gains will be pixel dependent, and we will have different values for different bands. So this scheme is actually based on such a multiplicative approach for defining the injection gains. And then we have several other techniques that have been proposed in the literature. And we're not going to detail all of them, of course, but the main idea is that we saw basically different ways to define the coefficients in the linear combination, generating this intensity component that should resemble a low pass version, a lower resolution version of the panchromatic image, and the way these injection gains are obtained. And basically, you can see that by taking that we have different techniques that have been proposed, and some of those start from fixing the gains and giving the same weight to all the bands, which is kind of a strong assumption, till for some more recent techniques, estimating those gains, those coefficients, for example, by least squares. And those techniques usually are those that perform the best in terms of accuracy, because they can adapt to the data that we have. And then the injection gains, again, we can see that the early approaches were just fixing them in beforehand. So just taking one, or like having them defined with respect to the data that we have. And in more recent approaches, we can see that those injection gains are dependent on like a kind of a measure of similarity between the intensity component that we have and the spectral band that we want to sharpen. And this, if you think, is kind of intuitive, because the idea is if we have a close match between close correspondence between the intensity component, which is the low resolution version in this approximation of the panchromatic image, and the multispectral band that we are processing, then it will be likely that the spatial details that we see in the panchromatic image should be present in that given band in the multispectral image. So those injection gain will be kind of adaptive with respect to the similarity between bands and the panchromatic image seen by this intensity channel, intensity image. So if we go now to present some techniques based that can be grouped in the multi-resolution analysis family. As we said before, the main difference with respect to the component substitution techniques is that the panchromatic image is considered for generating the details. So those details will be obtained by kind of a high-pass filter, or in an equivalent fashion to perform the subtraction between the original panchromatic image and the low-pass version of it, where this low-pass version of the panchromatic image is obtained by like a convolution of the panchromatic with a given kernel. So there are several techniques that have been proposed. So the first techniques that appeared in the 90s were just considering a box filter. So that means that this kernel here is just taking the average over a neighborhood for each pixel. And then other techniques considered a Gaussian filter. There again, we can find different injection schemes. So like an additive injection that resemble what we saw as well with the generalized IEEE-GRSS and the Provate transform for the component substitution techniques. And the multiplicative injection, where in this case, the injection gains are defined pixel-wise, and those are obtained for each pixel by the ratio between the value that we find in the multispectral band that we are processing, and the panchromatic, the low-pass version of the panchromatic image obtained by such a convolution. And there are like a lot of different techniques, as I said, that have been proposed, and so we have all kind of variants in the way we can generate a low-pass version of the panchromatic image, which will be a lower spatial resolution version of the panchromatic image. And so then we can use like a pyramidal decomposition based on Gaussian kernels or on wavelets. And something which is good to underline here is that if you think about like that process of reducing the resolution of the panchromatic image, well, that should be performed in a way that the spatial resolution of the panchromatic image that we have at the end of the process will be close to the spatial resolution of the multispectral image. And so that this processing shows good results when we consider some characteristics coming from the sensors, mainly using like the point spread function of the multispectral sensor, or equivalently the MTF, which is the modulation transfer function, which is just the modulus, the magnitude of the Fourier transform of the point spread function. So this will tell us in the frequency domain how the spatial frequencies, the spatial high and low frequencies that are present in the image will be transformed by this process here. And then, as I mentioned, we have several different techniques that have been proposed and based on wavelets, and one of the mother wavelet that proved to be effective in Pansharpening is the one that you see here, that actually happened to be very close to a Gaussian filter, where the variance or the characteristics of the Gaussian filter match the sensor MTF. So the point spread function finally of the multispectral sensor. So we, as I said, we can see different variations of that general model that we detailed in the papers. And in some cases, we see also some hybrid techniques, as in the case that you see here for the technique that is so-called AWLP, where the details are computed by performing a difference between the panchromatic and the low-pass version of the panchromatic itself. So those will be overall coming from the panchromatic image. But the injection gains are computed by considering the intensity component obtained as a linear combination of the bands of the multispectral. So there are really a lot of different algorithms that have been proposed, and those papers that I mentioned before that I invite you to have a look to, they will detail like a general framework where we can cast all those algorithms. So in order to recall those main, the characteristics of those two main families for the component substitution, the idea is that the details, the spatial details coming from the panchromatic are obtained as a difference between the panchromatic image and a linear combination of the bands of the multispectral image. And for multi-resolution analysis, we will have like a difference between the panchromatic and a low-pass version of it. And once these spatial details coming from the panchromatic are defined, it is possible to, with some appropriate weights, to inject them to the multispectral bands in order to generate a pan-sharpened version of that K-band in the multispectral image. So now that I gave you an overview on those classical approaches in pan-sharpening, then we can apply those to the images. We will get different results. And the main problem that we will face is how do we test the quality, how do we assess the performances of those different algorithms with respect to the images that have been sharpened. So quality assessment is usually done in pan-sharpening in two different ways. So the first, and perhaps the simplest one that we can put in place is the so-called reduced scale validation. So it's a validation done at a reduced resolution. So the idea of this scheme is to perform a degradation of the resolution of both the panchromatic and the multispectral image, and a subsampling. So in this case, we will have a copy of the panchromatic and the multispectral image that they were both reduced in terms of spatial resolution. And then we will process those reduced resolution versions of the original panchromatic and multispectral image. In this setting, the underlying idea is that once we were able to perform pansharpening over this reduced resolution multispectral image with the companion reduced resolution panchromatic image, we will have a pansharpened multispectral image which should be as close as possible to the original multispectral image. So as you can imagine, in this case, by performing this reduced scale validation, applying this scheme for performing a reduction of the resolution, it is possible to perform an analysis having a reference image that will be the original multispectral image. The second assessment procedure that we can find usually in the literature is the so-called full-scale validation. So in that case, the idea is that we take the panchromatic and the multispectral images at their original resolution, so as they were acquired by the satellites, and we will perform a validation of the pansharpening product based on some indexes that do not require any reference, which is kind of tricky because then we need to inject somehow some a priori information on what is, in order to encode what is a good result of this pansharpening product. So if we take the reduced scale resolution, then as we have an image, a reference image that we can use for validation, because that will be the original multispectral image, then we can compute all sorts of indexes that will compute a difference between, or a kind of a similarity, if you like, between the result of the pansharpening and the original multispectral image. And so we can find, for example, classical indexes like the root mean square error. That is the base of what we call ERGS, so which is an acronym of error relative globale dimensionnelle de synthèse. And also, for example, another classical index that is used is the spectral angle mapper, which is basically the angle between two vectors after normalization. So this index here is not sensitive to differences to scaling in terms of intensity, because we are normalizing the scalar product by the norm of the two vectors. And then we have other indexes that were proposed. So there as well, you will find several different indexes that are proposed in the literature. And here you can see 3 of those that are based on, let's say, kind of a structural similarity between images. That is a similarity accounting for both the average and the variance or covariance usually computed on patches of the image. And so you can see this general Q index that have been declined and defined in different ways according to the number of bands that we have. So like Q4 is usually for 4-band multispectral images, and then like that was generalized to an n number, 2 to the power of n number of bands. If we go if we account for the full-scale validation, as I said before, we cannot use a reference image because in that case, the ideal reference image will be the quest of Pansharpening. And so in this case, we can see that in the literature have been proposed indexes such as the QNR, so quality with no reference, where we have 2 main components, one usually that estimates the spectral distortion and one that usually estimates the spatial distortion. And then we have other that have been proposed, other variations. So now I would like to show some results on some real images. So here you can see a validation done in reduced resolution because we will have as reference the original multispectral image. Then we have the panchromatic and the multispectral images that will get fused in order to match this. That will be reduced in resolution. And I show you in this panel the result with respect to the reference image by using several different techniques that are coming from like the component substitution family and the multi-resolution family that you can see here. So it's not so clear how to see the differences in terms of the images that are produced. So we can have a look to a crop of that image, and you can see that with respect to the reference, some of the component substitution analysis techniques that are proposed show some kind of spectral distortion. So for example, here that region is not rendered in a correct way. So the colors that are shown here, or spectral variations, are not so consistent. And typically, what we see in the multi-resolution analysis is that the spectral distortion is lower, but actually the spatial details are not so rendered well as in that case. And this is also proven by the indexes like Q, the spectral angle, and this ergas based on the root mean square error. If we go on an example on a full resolution analysis, in that case, we will just have those 2 images, so the panchromatic and the multispectral. The multispectral could get upsampled to match the scale of the panchromatic. And there again, I will show you here some results of the techniques that I mentioned before. So in this case, we can also spot that there are some distortions between like some spectral variations in the family of the component substitution. And typically what we see is like the rendering of the spatial details is not so well done in the multi-resolution analysis techniques, which is clear if we take a zoom on the different images that I shown before. There again, we typically use indexes that require no quality in order to perform a quantitative analysis, and this QNR will combine the information coming from a spectral index and a spatial index. And it is possible to see as typically we have not so good results in terms of a spectral index for the component substitution analysis techniques, and for the multi-resolution analysis, then the problem usually comes from the rendering of the spatial details. So to conclude on this part, I shown some techniques and that are belonging to the component substitution and multispectral resolution analysis, and they are performing in different ways with respect to the Pansharpening problem. And as I mentioned before, like usually component substitution analysis are robust to problems related to misregistration between the panchromatic and the multispectral bands, but they are affected typically by spectral distortion. And this robustness in terms of the spatial domain is usually shown by having a higher quality resolution in the spatial details. Multi-resolution analysis techniques usually have the converse in terms of features, and they provide a good analysis of a good rendering of the spectral information, but they are typically providing poorer results in terms of the spatial details that are rendered in the image. So now I would like to end this presentation by providing some perspectives and some, let's say, an overview on recent trends that we can see in the Pansharpening community. So stemming from these classical techniques, we can see that there are the so-called third generation Pansharpening methods that have been gathering attention and getting more and more contributions. And those are usually provided by considering the formation model of those panchromatic and multispectral images in order to cast the problem of Pansharpening as a variational problem, so like an optimization problem. Some of those are also considering some sparse representation approaches in order to perform the Pansharpening problem. And recently, like neural network based approaches have been proposed, and usually taking into account convolutional neural networks or like generative models as well. So just to give you some details on the variational methods, the main idea is to base the analysis on a multispectral model that will rely the multispectral acquisition with respect to the unknown higher spatial and spectral resolution multispectral band, which is bands. That is the goal of Pansharpening. That will be a subsampled and blurred version of this higher spatial resolution and spectral resolution multispectral image. That will generate our multispectral acquisition. And then the panchromatic model, it will be kind of equivalent, where we can assume that the panchromatic band is obtained by a linear combination of the bands in the multispectral, in this high unknown multispectral image. And typically what we are doing in those techniques is to cast the Pansharpening problem as in a variational framework, where we define a cost function that should be minimized. So usually we have a data term and typically a regularization, because this problem is ill-posed. So we will have solutions that are not robust, or they might not even exist, or being unique. And just an example, a relevant example, here you can see a super resolution functional that is performing a sharpening according to the model of a multispectral image and the panchromatic image using some spatial regularization. So those are like some ongoing works that are providing providing results that are usually getting better than the classical approaches that have been proposed. So another like family of methods that we saw appearing in the recent years is based on convolutional neural networks, and the idea is there to learn an end-to-end model, so performing by reducing the resolution of the panchromatic and the multispectral image, and learning a way to super resolve both panchromatic and a multispectral image in order to generate a higher spatial and spectral resolution image that will be the result of the Pansharpening. So those are getting developed currently, and so they gather a lot of attention. And in terms of again of perspectives, we see several new axes that stem from the regular fusion of panchromatic and a multispectral image, where, for example, we perform like a sharpening of an hyperspectral image using a panchromatic image, and this is some scheme gathering a lot of attention in these days because we have some platforms that some new satellite missions like Prisma that has been recently launched that acquires an hyperspectral image and a panchromatic one. So the idea is, how do we perform such a fusion? And other alternative fusion schemes account for the fusion between a multispectral and for example, a hyperspectral or like multispectral images acquired by different satellites, so from different platforms. Okay, so this concludes the talk, and I would like to just underline that if you'd like to perform yourself some tests on Pansharpening, I can underline, I can propose to go and to those links where you can find some toolbox containing Matlab functions of the different techniques that I've been mentioning in the talk. Okay, so this is it, and I would like to thank you for your attention, and if you have any question, I would be really happy to reply.
Thank you, Mauro. Very enlightening presentation. I think especially the fact that you presented all these techniques under the same work frame is especially interesting. You were mentioning like these techniques as being 30 plus years old. Just a short comment. I started my master's in '86 with what was at the time the first Spot 1 image acquired over Canada. And to me, this is when all this Pansharpening business started. It was Spot 1 because we had 10-meter image but there was a fundamental problem is that we had Spot 1 had no blue band, had only a green, a red, and an infrared. And for the infrared, the sharpening didn't work as well, because the correlation, the overlap between the panchromatic band and the infrared is almost nil, and it was in the first satellite. Another, I think, interesting fact that I figured you weren't going to mention, but It's that nature actually uses the same trick, by fusing. Our brain is fusing information from the cones of our eyes and the rods to artificially increase, the sharpness of our vision. I'd like to make myself the devil's advocate a bit, saying that there are fundamental flaws in any pan-sharpening technique. And I'd like you to comment a bit on these flaws, see it from this angle instead of the advantages again, so just to look at the disadvantages.
Okay, so thanks for the sharing. I mean, your experience. So that is dating back to even earlier than the earliest reference that I put. That was 87,
Okay,
I think.
okay. Don't have to make a dinosaur or something. That's okay.
No, we say pioneer. Okay. So thanks for that, and thanks for the question. Yeah, I fully agree. I mean, as I mentioned, the problem of pan-sharpening is ill-posed by nature, and the result of pan-sharpening could, let's say, look good from a perceptual point of view. But if we use a pan-sharpened image for like remote sensing in a quantitative way, so as a metric product, in that case, yeah, we should do it with care, because I would like to underline that pan-sharpening will generate a synthetic image, so an image that was not existing, so something that has not been acquired by those sensors. And there are several pitfalls in the different techniques that we can apply. For example, as I mentioned, usually we have that the panchromatic can be associated to a linear combination of the bands of the multispectral image. And as you said, if the spectral response of the panchromatic does not match the spectral responses of the multispectral channels, because maybe some of the channels were acquired in an interval of the spectral domain that is outside the sensitivity of the panchromatic band, then in that case we could inject some spatial details that are not perhaps present in reality in that band. So that could be a risky process, because then we generate an image that is where we just added some artificial details that might look good, but they might not be meaningful from a spectral point of view. And something else that I saw from experience by looking at all those different techniques is that some of those techniques are coming from some heuristics or some first principle that have been then formulated deriving, let's say, a final algorithm for performing pan-sharpening. But those first principle basic facts come also from some interpretation of the data that we have. So sometimes, yeah, we perform like such a sharpening, but I think we should be careful with the results that we have. And this is even more true if yeah, sorry, just to finish.
Oh, sorry. No, just going to say, I'm glad to hear you say that, because I've been saying that to my students to be very careful about that, because the attraction is there. You see the two images, you tend to think, well, it looks better, but you have to think the loss of data as well. So I'm sorry, you if you wanted to keep going.
Yeah, no, just to recall that like data-driven techniques that are gaining a lot of attention in those days can provide also like very good results, but in those cases, the spatial details might even, I mean, we might even have lower control on the spatial details that have been produced, because those techniques like GANs based, for example, or also CNN, they are like providing astonishing results, but in some cases it's not possible to inspect in details the way they process the data, and then like we don't have so much control on the results.
I'm not sure, is there other question from the audience, from Jefferson?
Sure. Let's see. Laura, do you want to see? Do you want to? Can you please read for us?
Okay, great. Oh, Laura, oh, sorry. Okay.
Oh, you can talk.
No, I didn't get that.
It's a question from Jose Marcato Jr. Great talk, Mauro. How can we deal with positional deviation between PAN and MC images?
Okay, so thanks, Giuseppe, for the question. So this is indeed like a problem. Like we might have co-registration issues between the panchromatic and the multispectral channels, because they are, yes, acquired by the same platform, but then like they might be acquired with some lag, some temporal delay. And also, like in some nasty cases, we can, if there are moving objects like a plane flying in the sky, then in that case we will see kind of a ghost images of the object in the different channels. So the problem of co-registration in first approximation is not so much of a problem as if we were dealing with the fusion between images acquired by different platforms, but it is indeed present. So if we take into account the classical approaches, usually like the component substitution ones, as they perform like an extraction of the spatial details coming from just the subtraction of the panchromatic and the difference between a panchromatic image and a linear combination of the bands coming from the multispectral, they in a way account already for this misalignment between the panchromatic and the multispectral image. So in cases where this is a problem, then it would be better to use such of techniques in the classical framework, let's say. So I hope it replies to the question.
I'd like to have, because it has something to do with the same question. I saw one of the papers you co-authored that you actually, I don't remember the first author, but you actually took 60-meter data from Sentinel-2 and brought it down to 10 meters. And there, the problem of location becomes even stronger. You have to find a 10-meter pixel in a 60 by 60 meter pixels. If you can just comment on that study, I think it was from this year or last year or something.
Yeah. So if we take into account Sentinel-2, I think the main interest is in the fusion between 10-meter and 20-meter bands, because they all sense mainly land surface. If we take the 60-meter bands, in that case, as the 3 bands of 60 meters coming from Sentinel, they are designed for mainly atmospheric correction. So I think usually it's more of an exercise, I guess, taking them into account in the fusion than like to the real gain that they can provide in the fusion itself, because those bands are mainly for atmospheric correction, so they will see clouds or water vapor in the channel. But this is, I mean, your remark is valuable, because in some cases, like Pansharpening has some constraints, some limitations. We cannot like fuse 1,000 meter band with like a 10-meter bands, because there might be there is so much ambiguity that is not making the process possible. And so perhaps like the 60-meter bands can be helpful in kind of constraining overall, the consistency of the results, but then saying that we are able to precisely estimate the spatial details at 60 meters from 10 meters, then is a very challenging problem.
Like you said, it was a good exercise, but maybe not so practical in times. Okay, Jefferson, if you have another question, or Laura?
Yeah, I have a question, but first of all, I would like to pass my word to Laura. I will keep my question for the last time.
Thank you, Jefferson. Thank you very much, Mauro. Great talk. I learned. My area of research is deep learning applied to remote sensing image analysis. And for that reason, I would like to know what could be the limitations of using deep learning when compared, for example, with these classical methods. Sometimes we want to use deep learning for everything, but it's not always the best options. And then I would like to know your consideration about these limitations that we can face in Pansharpening with deep learning.
So in this case, deep learning techniques have proven to provide extremely good results. And so the talk was more like, let's say, an overview on the classical techniques, just to set a framework. But there are several examples where like CNN and recently like GANs provide very good results. One of the main limitations that I would say they have from a practical point of view is the computational complexity, because the classical techniques are, blazing fast. They are just a few lines of code, and you can process right away like very large images. And if we take the like another limitation that they might have, deep learning approaches, is that the main scheme, as far as I know, that is used for learning is end-to-end learning. So we reduce the resolution and we try to get back to the original images. And this, in general, is kind of sensor dependent, because if we have like a prediction model that has, or like a deep learning model for performing Pansharpening that it has been learned, usually like it focuses on a given set of images coming from a sensor. So if we process like 4-band images, then that model might not work on 8-band image. So there could be some problems related to like transfer learning, going from like a learned model on a set of images to another one, whereas like classical techniques are so simple that they can be easily deployed on different sensors. And I personally think there's very promising research topics that are related to joining or getting hybrid schemes based on data driven techniques like deep learning approaches, and also considering as kind of prior knowledge the results that could be given by classical techniques as well.
Yes, I was thinking about the robustness of classical models could be better than deep learning models. Thank you very much for your answer.
My question is quite related to this. And did you see those methods that perform super resolution, for example? When I see this kind of approach, I usually relate this with Pansharpening. What do you think about it? It's possible to benefit from super resolution methods to solve or to improve Pansharpening approaches?
Yes, definitely, because we could think of like Pansharpening as a simpler problem with respect to the super resolution, the classical super resolution that we could apply, because in super resolution we have no reference, no guiding like information that could come from a higher spatial resolution version of the image that we want to estimate. And in that case, I mean, having at our disposal a panchromatic band can be really beneficial because it will guide the super resolution process on the multispectral images. Then the question is like, how can we exploit this information as it is not directly related to, doesn't match in a straightforward way to the higher spatial resolution multispectral image that we want to estimate. So that is, I think, like, yes, definitely we should use that in order to perform super resolution. So it could be an improvement to classical super resolution problems. And then the open question would be like, how do we put them together? Which could be what Laura, also joining what Laura mentioned before, like that by designing some deep learning techniques, then we can have like this freedom in putting together the information coming from the panchromatic and the multispectral images.
Yep. Thank you. So, Philippe, what do you think? We are quite finishing our session, but we have time for one question from the audience. What do you think?
Well, I had something I'd like to run by Mauro. It's just an idea that
Okay.
I was thinking of. I'm no specialist of Pansharpening, but imagine we've been using with high resolution image or very high resolution image, the segmentation inserting segmentation before classification. So you separate the objects. How about performing Pansharpening only on edge pixels after maybe a segmentation? I don't know if this has been done or tried, so that you preserve the information within the objects, but then you use Pansharpening to only on the edge pixels. And this came from a project I had. We used Sentinel-1 images, real images, to extract the contour of small lakes, and we quantified the proportion of water and ground within the edge pixels. And so I was thinking something like that. What is your feeling? Or it maybe has been done. I don't know.
I think it could be a good approach because the regular conventional Pansharpening approaches are kind of unsupervised by definition. Like the goal is to generate a super resolved image, but this process is not optimized with respect to a given final application. So if the final application is to perform some land cover analysis or land use analysis in order to detect some specific classes or objects, then there could be definitely the possibility to embed this information in the process. And this could be done, as you said, by performing kind of a segmentation on the image. And we worked a little bit on that, and in order to estimate the injection gains based on some segments. So the idea was to segment the image and estimate like a coefficient that was weighting the different details that were injected in an image. That was based on like a segmentation. So each segment in the segmentation map was using the same injection gain. And that was a way to perform the process in an adaptive way with respect to the spatial content of the image. But this could be definitely go further away if, for example, you would like to process mainly vegetation. And then, as you mentioned before, perhaps blue bands or like green bands are not so well rendered because they perhaps due to some mismatches with the panchromatic spectral response. And then by detecting those areas beforehand could be a way to perform in an adaptive way the Pansharpening process. So in order to enhance some specific bands that could be that we could know a priori that they are more important for generating that kind of land cover. But
well, might be an idea to test, something to test. Okay, thank you, Mauro.
Okay, thanks.
Jefferson?
So one more question?
Yeah, sure.
Okay.
Sure.
Hi, thanks for the presentation. What is the effect of the size of the test area in the Pansharpening performance?
I would say that is quite limited in a way that the techniques that are applied perform a local analysis. So let's say the gains or the way the multispectral and the panchromatic image are put together is usually dependent on like a close neighborhood of each pixel. Like a stronger effect could be done if we consider very large areas. If some of the assumptions that we are taking so far are not true, for example, the fact that the point spread function of the multispectral band is translation invariant. So it will be exactly the same in all parts of the image. But if we take a small crop of the image, this can be seen as in first approximation as a property that holds. But if we consider a very large area, in that case, we might experience that the blur, so the point spread function will vary with respect to the different part of the image. And this is not intrinsically taken into account, but by the techniques that I mentioned. So it should be something to consider. But I would say in first approximation, perhaps this is not so, it doesn't give so much of an impact, but this is something to take into account if we are going deeper in the models that we consider for performing the Pansharpening.
Oh, thank you. So I believe we are done. I believe it's all of wonderful in this session. So thank you, Mauro. I would like to thank also Philippe Maillard for the partnership here, and also Laura.
Very good. Thank you, Mauro.
So
okay.
Thanks to Jefferson, thanks Philippe, thanks Laura for chairing the session, and to all organizers and the audience that followed. And
you're in Grenoble, is it?
Yes.
You're in Grenoble? Okay. I I go to Saint-Hilaire a lot. Near,
You went to? Ah, okay.
I go to Saint-Hilaire. I do hang gliding. Hang gliding.
Paragliding. Yes.
Yeah.
So give me a call next time that you come.
Sure. Okay.
So
Good luck
I'd
to
like
you.
to thank the audience also, and see you. Bye bye.
Okay.
Bye-bye.
Bye-bye.
Thank
Thanks.
you.
Bye bye.
Thank you. Jefferson.